I'm going to talk about homework problem number 8. Okay, in that problem you had a 5% incline. We depict that incline. Now, this is way more than a 5% incline. Okay, if I take this as a portion of this, this is closer to a 35% incline than to a 5% incline. But for representation, I want to be able to draw projection vectors that you can see. So I've kind of exaggerated the incline. So we're not going to make any estimates from this picture, but we're going to calculate the estimates. And we're going to calculate the quantities. Okay? So here we are on the 5% incline, and I've told you that the weight of the cart is 0.5 newtons, and your W vector is therefore going to have magnitude 0.5 newtons. Its projection is going to be here. Again, greatly exaggerated. It'll be about maybe 1/6 of that length. And you also, have the projection on the y-axis, and I've kind of labeled the W in an unfortunate place, but right here is your W perpendicular vector, and here's your W parallel vector. In the absence of other forces, your normal force will be equal in magnitude and opposite in direction to your W perpendicular vector. So you're going to have a normal force up here. It's not quite long enough, and I'm going to use F sub n. A lot of times just plain old n is used for the normal vector. Just for clarity, I'm going to probably usually use F sub n. So the picture isn't anywhere near to scale, and this vector is somewhat too short, but we still have a depiction. Okay? And the magnitude of F sub n is approximately equal to the weight. In the magnitude of W parallel, let me just write that as plain old W parallel with no vector over the top of it, is about 0.05 times the magnitude of W, which is 0.05 times 0.5 is 0.025 newtons. Now, some people approach this by taking this 5% incline and calculating the angle so that you could use the formula, which is something like the parallel component here is equal to W times the sine of theta, where theta is this angle. I prefer to use I'll do most of my explanations using the circular model, in which case it would be the cosine of 270 minus theta, but of course that's equal to negative sine of theta. And notice that we get the negative. We don't have to think about whether the negative. All we got to do is think what the angle from the x-axis around to this vector is, and we can do that. Okay, that formula, W sine theta, if you just habitually use that formula without thinking about what it means, I think it's going to be more error prone. In any case, even if you use that formula, you should think through the triangles and so forth, and be very careful in assigning the correct plus or minus sign to everything. But that's totally unnecessary, okay? And given the information you had, you wouldn't have wanted to do that, okay? What you're doing in that case, and believe me, I perfectly well understand it, is you're grabbing onto something you know very well and applying it to the situation because you know it's going to work, okay? You can sort that out as best you wish, but more than one person did that and did it correctly. So, you know, no real criticism here, just you don't want to be too formula dependent, okay? And it makes me a little uneasy when a formula gets pulled into an equation or into a problem when it's unnecessary. Okay, so anyhow, we got W parallel equals 0.025 newtons, and we have, and I have to flip back here for a second, excuse me, but Where in the world is it? Okay, I think we had a 2% coefficient of friction. I just want to double check that. Yep, 2%. Okay, I had to flip over in the computer there for a second. So that force of friction equals what? It's going to be 0.02 times Fn. No, won't put a vector over that. This is one place where you do have to decide on the direction of the force. Okay, so the 0.02 Fn, well, Fn is equal to W, and that's .01 newtons. And I think everybody got that one way or another. Okay, so again, no problem. Y'all did, as a group, quite well in the problem set. The only problem that gave you any major difficulty, I think there were 2 people who did some pretty good work on that problem, and everybody else pretty much gave up on it. And that would be problem 10. And I assigned that problem knowing that that would be very likely a difficult and challenging problem for many of you. So if you got the first 9, excuse me, I think despite the glitches we've had with class time, y'all are doing okay here. Okay, so the frictional force is 0.01 newtons. And now we want to consider what happens if the cart is moving up the incline, if it's moving down the incline. So if up, the force of friction equals 0.01 newtons times negative of the I vector. I could have put that negative out in front, but I was thinking it, but I didn't put it there. Might have been better out in front, but either way it's okay. The negative I direction is here, so the negative I vector is in this direction. And if the cart's moving up the incline, that's going to be the direction of the friction. So either way is okay. W parallel is negative 0.025 newtons times I. So the result, or the net force, is negative 0.025 newtons times I minus 0.01 newtons times I, which is negative 0.035 newtons times I. Again, everybody that turned the homework in got that. But I want to put that in the context of the vectors. You want to be very careful to get the direction correct, because this is a frequent pitfall. Okay? Frequent isn't quite the word I wanted, but the right word never did pop up. Okay, if up the incline. Okay, if down the incline, then dot, 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 similar argument, and you get F net equals plus, well, negative 0.025 newtons, which is the same as before, because that component of the weight vector is not going to change depending on the direction of motion of the car. That component of the weight vector is what it is, and it's constant. But then our friction, if the car is moving down the incline, the frictional force is back this way, so we get plus 0.01 newtons times I, and that's negative 0.015 newtons times I.